Thank you, Shikhar. After the tech journey, let's talk about the ML architecture. So this basically sums up the few previous slides which we have been talking about. So what happens to an address string when it comes in? So the ML architecture consumes the string and breaks the input string into a set of tokens. That is the tokenization process. And once we have these tokens, we send each of these tokens to feature extraction. So features are made token wise, and once we have the features, we encode them using one hot encoding of top k words, and all this has been explained in the previous slides, the encoding, the extraction process. But and once this encoding is done, you have your input matrix for an for an machine learning algorithm. So these encoded features are stored in an H2O frame for a batch of addresses. So generally, in our case, we took the batch as 1 lakh addresses, and generally, uh, an address had around 9 to 10 tokens on average for United Kingdom. So basically, this H2O frame at one go will have around 10 lakh rows. So one row corresponding to each token, which stores the encoded feature set for every token. And once that is done, it is fed to the trained machine learning algorithm, which has all the optimized weights, and hence we get the class of the respective token. Let's move out. Let's move on. Um, so ML projects are not very straightforward. So we did not know that a deep learning and a deep neural net was the best solution for our use case, and hence we ended up experimenting quite a bit to arrive at this deep learning solution. So this slide talks about the various experiments which we did, and I'll also talk about the intuitions behind these experiments. So the first one was multi-level modeling. Now, multi-level modeling uh, was derived from the intuition that our initial model was identifying the boundaries of the classes really well. Now, what I mean by this is so the address on this slide, flat 16, Grafton House, William Street, London. So even if our classifier got certain tokens wrong, uh, the boundaries were identified really well. So let's say our model identified Grafton House as a postcode, but at least it identified that Grafton and house tokens have to come together in a class. So this intuition was to be exploited. So what we did was, first we identified the buckets. So on the first level of class, so this is a multi-classification problem, not multi-class classification, but multi-stage classification. So what we did was we identified flat 16 as a bucket, Grafton House as bucket, and various sets of tokens in different buckets using BI tags, that is boundary and insight. And once we had these buckets, the only task left was to label these buckets. So once you know flat 16 comes in one single bucket, you just have to label it as house number. So you identify the segments and then label the segments. Uh, and an important feature to identifying these segments was number of tokens in the segment. So, for example, postcode generally has one or two tokens at max in the segment, whereas a road or a street class might go up to four or five tokens. Uh, and Then we also experimented with an ensemble of random forests, which is gradient boosting. Gradient boosting gave us a little inferior results, but complementary at the same time. So what we observed was there were a few variations in which our base neural net model wasn't able to classify correctly, and XGBoost come to the rescue. So when the neural net faltered, the in some cases XGBoost performed really well. But overall, on a varied test and a validation set, XGBoost XGBoost accuracies weren't at par. Then we also devised an algorithm which was totally in-house. That is the third one on the slide. That is word frequency. Now, word frequency borrowed concepts from TF-IDF and naive Bayes to solve our use case. So, what we did in this case was we shortened the process of feature extraction and encoding by first iterating over the data set and forming a vector corresponding to each token. And the intuition was, so for example, a token called London is most probably expected to appear in city, and a second highest occurrence might be in street. So for example, London is a city, and there might be a few roads called London Street, London Lane. So basically we tabbed the occurrences of a token in various fields. So we had 10 classes, and let's say London occurred 10 times in an organization, 100 times in city, and 50 times in lane. So we can form a vector based on these occurrences, and we can do this for all of the tokens present in the dataset. And once that was done, we can get a probability of occurrence of a token in a field, which is analogous to the prior probability in the naive Bayes algorithm. So you basically you have a vector corresponding to each token, and while classifying, you can just get that vector, modify it a bit, and store it in your data frame. So, but we didn't end up pushing this model to production because there were quite a few tokens which were not seen in the reference data set, and so we had to drop it because of a little lower accuracy levels. And then we also thought of ensembling all these techniques and yeah, implemented a POC on that as well. But the uplift on the accuracy was not sufficient to compensate on the cost of performance, because in an ensemble you have to run the base models and then do your ensembling on top of it. So basically it's more computation for the pipeline. Let's move. Yeah. So this slide talks about the post ML step, the last in the machine learning pipeline. So the task of this stage in the entire pipeline was to bring in certain domain knowledge and manual rules to correct the predictions made by the machine learning model. So, for example, if we have an address called a flat 16 Grafton House, William Road, the postcode and the country, and say the postcode got predicted wrong, that is the 3DF part, got predicted as country. Now we have a regex, a regular expression for the postcode. So we can, after the predictions have been made, we can just uh, go and check if the prediction matches that regular expression, and if it doesn't, we just make that prediction as unpassed. So this uh, prediction gets converted to unparsed, and we save the machine learning model from making a mistake. Uh, ML systems generally tend to get a lot messy as well as complex as the code base increases, and the complexity of algorithm increases. Now, and we had identified this from an early stage. So we devised an intelligent debugging technique through metadata, and I'll show this through a demo. So what I mean by this is, when an input address comes, and there were certain changes made in the to the address in the normalization in the pre-ML stage, and then predictions were made and confidences were calculated. Now, if we want to evaluate the addresses on which our model is not performing that well, we need to have an intelligent debugging system. We cannot always go to the code base and look where the model, or where which part of the pipeline went wrong. So let me just so this is our application, and I've entered this address, flat 17 Grafton House, London, and the postcode. So for the debugging purpose, we also publish a metadata. And when I clean this metadata, you can see something like this. So when we go and skim through this metadata, we see that there were certain modifications done to the tokens, and these tokens help us evaluate where the changes were made. So whenever a faulty address comes up, the first thing our developer team does is to see the metadata, and it gives us a lot of strong intuitions as to which part of the pipeline went wrong. Uh, yeah. So coming back to the slides, um we also have I'll just go back and show you. We also have confidences attached to the various predictions we make, and the intuition behind these confidence scores is derived from our base module in Spectrum, that is global address validation. So, what global address validation does is, if it is not confident about certain addresses, it it gives it a low confidence, and addresses passed below the threshold confidence are tagged as invalid. So we wanted a similar mechanism on our front as well, where the addresses which our ML system was not confident about, we wanted to give them a lower confidence. And also a threshold of 80 was set because GAV followed similar pattern. An address passed below the confidence of 80 is generally should be ignored. The parsing should be ignored. So the confidence scoring mechanism was like this. So on the left hand side, the word frequency model, which we which I talked about in one of the previous slides, though we ended up dropping the model for classification or for predictions, but we still kept it for calculation of confidence scores. So what word frequency confidence gave us was the probability of occurrence of that token in a particular field. So that confidence combined with the ML confidence. So ML confidence was basically the distance of the point from the hyperplane. So what that means is if we have a decision boundary or a hyperplane, and our classification, that is the point, has a larger distance from that hyperplane, it means that that the ML system is fairly confident of that prediction. And if it is near to that hyperplane, it means that the point can go to the other side of the boundary, and the prediction can change with a very small change in the ML system. So that gives us the confidence score, and we aggregate both of these confidences through different weights to get an aggregated confidence. And once we have that, we calculate the confidence for different scores by taking the minimum. So what that means is, say we need to calculate the confidence of place name, and place name had three tokens. Say the Buckingham Palace. The was tagged as place name with a confidence of 70. Buckingham was tagged with a confidence of say 80, and Palace was tagged with a confidence of 90. Then the confidence score for place name tag would be 70, because that is the minimum of the tokens. And similarly, we can assign a confidence score to all the classes. Um, and this slide talks about the ML building process. Once we have done our offline training in Python using the H2O framework, we generate the final optimized model as a plain old Java object, which is consumed in our Spectrum code base as a Java class. We package it using Maven, and use the model in our code base. So this slide basically uh, uh, takes in shows the an input address going into the deep learning classifier, and tagging various tokens in different classes. Now I'll start with the performance metrics, and how does the model which is running in production in 12.1 in compares in terms of accuracy, performance, and to other traditional systems which are in place in Spectrum. So uh, the accuracy metrics which we took to evaluate the accuracy performance of our model was token wise accuracy. So if an address has 8 tokens, and we predicted, so if an address has 10 tokens and we predicted 8 tokens correctly, the accuracy of our model is 8 by 10, that is 8 by 10 into 100, that is 80%. So the accuracy is 95% on the validation set, and 93% on test set, and the split is 50 25 25. So what that means is, if we had 100 addresses in our data set, we devoted 50 addresses to training, 25 to validation, and the rest 25 to test set. And which is actually a very good number as far as a machine learning model is concerned. And the throughput, or the TPS, was 2000 addresses, so we were able to So the machine learning system was able to parse 2000 addresses in a second. And this confusion matrix is just for the, it's not the real matrix, it's just for just as an example. But the numbers cited, the accuracy numbers, are the actual numbers which we are getting right now. So because the diagonal elements on this confusion matrix are on the higher side, this generally indicates that we are performing really well while predicting different components of the address. Now, this slide basically is a ground for the QA or the performance number evaluation. So the token-wise accuracy was to evaluate the machine learning system, but for the product, the address parser product, we generally used three metrics. So an address has the components listed in this slide. For example, the organization, place name, unit, house number, street, and these are eight components. And if the machine learning model, if the machine learning system was able to predict all these eight fields correctly, we place them in exacted category. If we were able to uh, parse 7 to 8 components correctly, we place them in 7 to 8 category. And subsequently, if we got more than two components wrong, so for example, if we predicted organization, place name, and unit, all of them wrong, so we were able to just get 5 components correctly, we place them in less than 6 category. Now, this slide is basically the evaluation of the ML system on different data sets. So, on the geocoding data set, which had about 11,000 addresses, um the machine learning model was able to parse 73% of these addresses, uh, uh, what it means is that the machine learning model was able to parse 8 out of 8 components in 73 addresses out of 100, which is a good number. In 18% of the cases, the model got one or two components wrong, and very rarely, that is 9%, the model got more than two components wrong. And on the Dun and Brad dataset, that is the DNB dataset, 46% of the times, all the fields in an addresses were passed correctly, and 33% of the times, the model got one or two components wrong, and subsequently the other number. The reason for this was that the number is slightly lower than geocoding dataset is because the baselines were not correct in this dataset. Also, this is a relatively harder data set to parse, and UK is obviously a difficult country when it comes to address parsing. So all these components combined lowered the number to 46%. And for Germany, in the geocoding dataset, 70% of the times all the components were tagged correctly, and 24% of the times we got one or two components wrong, and very rarely, that is 6%, the components were less than 6. Now, uh, so just as a background, locate is a traditional, already existing address passing mechanism, which is purely rule based, which already exists in Spectrum, and the aim was to develop a parser which obviously beats the traditional system by a good margin. So to evaluate the performance of the machine learning based address parser to the rule based locate, we did a certain analysis, and what this slide shows is that while evaluating both of them on Royal Mail dataset, which had about 50,000 addresses, a clear cut 15% improvement was visible when it came to parsing as compared to locate. So we the address parser was able to parse 70% of the addresses fully with all the eight components correct. Locate was able to parse just 55% of addresses with 100% accuracy. And in case of Germany, this number, this margin grew a lot, and about 60% improvement was shown. Um, so in case of Germany, eight components were passed correctly for 76% of the addresses, and in case of address parser, and only 14% of the times for locate, which is a good number. Now, there's always so the main intuition to build an address parser was also to help address validation. Now, just as a background, address validation is the process where an input address is validated against a reference data set and then tagged as valid or invalid, which basically means that a parcel or a letter is actually deliverable to the address. So if an input address comes and the software tags it as valid, what it implies is that there is an actual address with that, and the address is actually deliverable. So one of the reasons of developing address parser was to uplift address validation. So if you have better parsed address components, you obviously have a better chance of validating the address. So Spectrum already has a address validation system, that is the GAV, in place, and what we did a small a POC, and preceded the address validation stage by the global address parser, the machine learning based global address parser, and tried to analyze if there was an uplift in the confidence of the validated addresses. Now, again, as a background check, GAV validates addresses if they are validated with a confidence above certain threshold, which is 80%. So after parsing, if that confidence increases and certain addresses which were valid but were validated with an address with a confidence lesser than 80, after passing, if the confidence increases to 80, this is a sure shot win for the address parser. So, the first point shows in case of Germany, 67% of the addresses had an increase in the confidence. So, which is a good win for the address parser. Also, there were a very few addresses which were not which were valid earlier, but were invalidated by the address parser. But on a deeper analysis, it came out that those addresses were actually false positives from the address validation. So what it means is that those addresses, though were invalid, were being validated by the global address validation. And after parsing, their confidence decreased. So again, it's a win for the address parser. And so basically, address parser helped in reducing the false positives of the address validation, which is actually good. And for UK, a major uplift wasn't observed, and that's because GAV is custom made for UK addresses, and generally it performs very well for UK data. So there wasn't much scope for improvement. Now the next 2 to 3 slides will quickly skim through the other use cases of address parser apart from apart from the uplift in address validation. So there is this use case of financial crimes and compliance, that is FCC. Now, if a fake address comes in and it is just passed through the global address validation, you'll just get the address as valid or invalid. But if you pass it through the address parser, you can have various filters. So for example, if an organization got tagged as dummy company, you can just put a small filter and report to the client that these organizations from the invalid addresses are fake. So what it means is, instead of giving the whole address, you can give out a detailed analysis to stop the fake accounts. Also, there's this use case of auto correction of multi-line input. So input which are multi-line can be easily concatenated into a single line string through address parser, and we can have a better level of granularity of parsing and a more accurate level of parsing. And this is a really good use case. Uh, and So as you can see on this slide, there were the multi-line address was split into two address lines. It was concatenated into a single line and then parsed through the address parser. And finally, if you have a bunch of addresses, you can pass them through the address parser and then run another module of Spectrum, that is data profiling, on top of it. And you can get the analyst can get a deeper insight into the address data. So for example, you can get the frequency of postcodes, and also you can have how many times an organization or a field or a component is occurring in a particular field. And moving forward, we plan to build an address validation system on top of address parsing, because the real revenue comes from address validation. And also there are plans to add more countries to address parser and make it capable of catering lot more countries than it does presently. And that's it. The stage is open for questions. Thank you.